you've made my presentation a lot easier. I think many of you would realize why we changed the order of the talk. So my talk is on ensemble forecasting of Streamflow out to 12 months using climate forecast as input. I'll start with a brief context because Julian has done most of that anyway. And I'll talk about the Fox model. In particular, I will emphasize how we use the GCM seasonal forecast for Streamflow forecasts. I'll present some of the evaluation results and make some conclusions. Julian already talked about the current operational service using the BJP model, but also a dynamic model. When we developed first, the model was very much purely a statistical model, but later on we started to incorporate some of the outputs from dynamical climate model and also hydrological model. Julian mentioned that the Bureau started operational service started in December 2010, and we've had some quite positive feedback from the water industries. The Bureau has done 2 formal surveys, but we've had a lot of informal interactions, engagement with our stakeholders. And while they're very positive about our work, about the Bureau service, they want more, basically. They said, well, can you break down the 3 months total, the forecast of 3 month total volume into monthly, because we really want to have monthly values. So that's one. And secondly, they said, well, we really want you to go out 12 months. We want you to go 12 months. 3 months is not enough, because when we do our planning, we go for a whole year. So 3 months is not enough. So currently, with your 3 months total, it's a bit hard to actually use, especially quantitatively. So this is really, this work I'm going to talk about is really about addressing that user need. So the Fox model is for generating forecast-guided stochastic scenarios. So that's how we gave the name Fox. So it's forecast-guided stochastic scenarios. So this may not be exactly the usage Bryson talked about, the scenarios, but we got forecasts and scenarios in one. So essentially, it's ensemble forecasts of monthly volumes of Streamflow out to 12 months. And the forecasts become more like natural stochastic series as the skill increases with lead time. So if you imagine that a water utility would use stochastic series, as some of them do, a purely stochastic series to do their planning. And now what we try to do is to narrow down that stochastic series, especially in the first few months, narrow down that range. So you have these seamless forecasts and stochastic elements to it. So to get this right, we really need to have a few things happening. We want to have the skill of the forecast as good as possible, so we narrow down the scenario range. And secondly, we want to have, when we don't have skill, it does become more like climatology scenarios. And we not only need to have individual month right, but we also need to have the connections between different months. So we have the persistence of the flow correct. So you get, when you sum up the volume, you also got your uncertainty right and so on. So this is really what we're trying to develop. And the Fox model has got 2 components. So this is very much a dynamical modeling approach that Julian talked about. So the first component is about forecasting rainfall, getting the rainfall forecast. And second part is about hydrological modeling. And today's talk I'll emphasize a bit more on the use of GCM forecasts for generating rainfall forecasts, just because the nature of this conference. So for this work, we first generate the monthly catchment rainfall out to 12 months. So we use a method called Cband to post-process GCM seasonal climate forecasts. So the particular GCM we use for the results I'm going to show you, we use the Australian Bureau of Meteorology seasonal climate model. I think Yuri may talk about the use of that model, describe that model. And the method we use to post-process that GCM forecast, we use Cband, and it stands for calibration, bridging, and merging. So why do we need to post-process GCM seasonal climate forecasts? The forecasts, we know that they generally don't really like real rain. So we have a bias, both unconditional bias and conditional bias. We also know, so the Parma and all other GCM now generate ensembles, but we know that ensemble spread tend to be not representing the real uncertainty. So we need to do something. Most models tend to be too emphatic, so the spread is not wide enough. So we need to fix up the ensemble spread. And we also know seasonal sort of type forecasts, the skill is pretty low still, in particular for rainfall. So the question is, can we extract more information out of GCM? Can we improve? We know that the GCM community has been working really hard to improve it, but we may have to wait another 10 years before major improvement. We're going to see that major improvement. So in the meantime, can we do something to extract more skill out of the GCM? And of course, for seasonal Streamflow forecasts, we also need to match up the scale as well, because GCM tend to have much larger spatial scale. So I will show you some of the major concepts in the Cband methodology. And I'm showing you in the continental scale. So later on, I will talk about how to translate that into catchment scale. So calibration, essentially, we have the raw GCM forecasts. We want to make it to become more like real rain forecasts. That is to correct the bias and also get the ensemble spread right. And the method we use the BJP, the Bayesian joint probability method. Initially we developed for Streamflow forecast, but we actually saw a utility here as a statistical method to translate that into calibrated rainfall forecasts. And here we use the ensemble mean of the Parma as the rainfall. Now I talk about the GCM underlying skill, still very poor in terms of rain precipitation forecasts. However, we do know those GCM tend to forecast the large climate patterns reasonably well. But the GCM, the climate model, don't necessarily translate those sea surface temperature or large atmospheric patterns into good rainfall forecasts. So the question is, can we make use of the good sea surface temperature forecasts and then statistically bring that into rainfall forecasts? And so we use the sea surface temperature as represented by a number of climate indices. And then we also use the statistical means to forecast rainfall. And so we have a number of, we call this bridging. So we have a number of predictors we use for Australia, and we have a number of bridging models. And in this way, so we try to make good use of the GCM forecasts of sea surface temperature. And we do know some of these have better skills than directly using the GCM rainfall forecast, even after calibration. So the next step is to merge the calibration and merging, and the bridging forecasts. And in fact, there are a number of bridging forecasts. So we use, in this case, we use the BMA, and the QMA work sort of came later. So essentially the idea is for some season, for some locations, the calibration rainfall forecast may do better than the bridging forecast, and in other locations, other seasons, the bridging forecast may be doing better. So by looking at historical forecasts, then you can put more weight on the better performing models. So in that way, you take advantage overall the better models. So I demonstrate those concepts in the continental scale. For catchment scale, we need to do downscaling. So in this case, really your predictant is the catchment rainfall. So the methodology is pretty much straightforward. However, we apply the method for different lead times. I talked about early on, we forecast the out to 12 months, the monthly rainfall. So we have those models separately for different lead times, but we need to piece them together to link them up. And for doing that, we can't just do that randomly, because you might have a dry month followed by another relatively dry month and so on. So we use a method developed by the US National Weather Services, the Shaky Shuffle, to do that job. So that gives us the persistence, right? So then you have ensemble time series of rainfall forecasts. Our next step is to put those rainfall forecasts through a hydrological model. And in this case, we use the monthly water balance model, and that's called UPABA model, which we published back in 2011. So that's our stage one. And in stage two, we look at it's really based on the hydrological model. Some of the month, the model does better than other months. Even you have the perfect rainfall forecast or using your observed rain as input. So we want to make some bias correction for different months, conditional bias correction. So in that way, we actually are able to improve the results quite a bit. And the stage three is making use of the latest observed strength flow, so the observed strength flow in the last month, and propagating that information through your forecast. But also, very importantly, is adding the hydrological uncertainty at each lead time and propagate that. So in that way, your overall uncertainty is both the rainfall uncertainty, which we try to get the uncertainty right, but also getting the hydrological uncertainty. So I'll talk about how you get the strength flow, the need to get the strength flow uncertainty right, and so on at the end. So we actually developed a procedure for injecting and propagating that hydrological uncertainty out to 12 months. So I'm going to show you some evaluation results. We initially looked at 20 sites across Australia, and we're currently actually evaluating on more sites. And all the results I'm going to show you are the is the 5-year cross-validation using what Julian has described as the 5-year live 5-year out cross-validation. So I'm going to show you one particular catchment which gives us relatively good skills. I'm going to show you the good results. So this particular catchment is in Queensland, and here's just a plot, a monthly stream flow, the variability in different years and throughout different months. So here the range is 10 to 90 a range, and here's the mean, and here's the median. So what you can see is there's a huge variability in some of the seasons, and also there's a very distinct dry and wet season cycle. And here are two examples, the kind of forecast the model would generate. So here we have the beginning of the forecast. So here is actually really a hindcast, so for particular time. So this is a 12-month period, and started from a particular time. So basically the fainted lines, each one is an ensemble member. So that's give you one possibility, or using the term one scenario. So I've only plotted it 10, but we actually generate about 10,000. And the black line is the forecast median, and then the darker shaded range is the 50% credible interval, and then we have the 90% credible interval. So this is just give you a range. So the whole idea of this is, with each ensemble member, a water utility can take that and input into their water planning model, so they can run that. And for a particular management strategy, they can work out what is the outcome if they use that particular management strategy under that scenario. And then they can pick up another ensemble member and they run that through. So at the end, they can analyze what is the outcome in probability terms if they apply a particular management strategy. So this is why the water industry has been asking for this kind of information. And here is just another example of the kind of forecast we might actually see. So red is actually for that particular period what turned out to be the red. Julian talked about forecast skills. So here is the continuous rank probability skill, and this is for each month. So here we have the y-axis is the forecast target month. Now we have 12-month forecast out. So here is the forecast lead time 0 1 month, 0 month, 1 month, and so on. So when we say 0 lead month, essentially the forecast at the start of December, for December, so that we call lead time 0. And here is forecast for December, but our forecast is issued in 1st November, and so on. Now the skill scores here, so they are the CRPS, and they are with respect to what the climatology would be, that is climatology stochastic series. So if you imagine that if your forecast is purely stochastic scenarios, then the skill would all be white. So there's no skill basically. So that's your reference point is skill is white. Where there's a blue, that means your forecast actually is narrowed down the forecast range. So it's doing better than the climatology. And where the red, it actually means you probably got something your model is not doing quite right. And as you see early on, I talked about stage 1, just pushing through the rainfall forecast through a hydrological model. We do have some months, we have some trouble, but after a bias correction, conditional bias correction, we're actually able to remove the red. We also increase the blue area. And when we use updating, we further improve the forecast skill, and in particular, the very short lead time. Now, we want to know whether we got our forecast uncertainty right. And Julian showed very quickly a probability integral transform plot. I want to explain what it is. Basically, if your forecast uncertainty right, we should expect the points to be along the perfect one-to-one line. So here is the forecast for January 0-month lead time, and forecast for January the different lead times, and here's for July, just as example. So what you're seeing is actually we got the uncertainty pretty right for each month in terms of the uncertainty spread of our forecast. Now, I mentioned about for water planning, they're not just looking at individual month. They also want to look at how the month cumulatively do to your system. So here we look at how we're doing if the forecast doing in terms cumulative volume. So here we have the forecast starting month. So this is the forecast starting from January, and accumulated over a month. So that's the January forecast. And here's accumulation over 3 months. So it's January, February, and March, and so on. So 6 months and 12 months. So the different. So we look at the skills in terms of accumulation. And this is the stage 3 forecast. Now what you see is compared to the monthly volumes, the accumulation has a much better skill than the. So this is because for individual month you have a lot more randomness, so your forecast is much harder. But when you accumulate that, you cancel out a lot of noise. So there's more signal in your forecast. So we're doing much better, and we think for water resources management, this is actually more relevant. Yes, we really want to get individual month volume right, but if we can't, at least we should have some useful skill in terms of total volumes, cumulative volumes. And we also want to check whether you got the accumulation right, because if you get individual month right, but you don't get the connections between different months right, then you're going to have a very narrow range because the randomness cancels. So you really want to have the good persistence in your forecast. And what we see for cumulation, we're actually pretty right in terms the reliability, in terms the forecast uncertainty. So we're very pleased with that when we saw that result. Now, early on I mentioned we've done 20 catchments, and so this is the CRPS skill monthly stage 3, so monthly volume. And I did warn you that, well, I gave you a good example, which is this. So what you see is the skill for seasonal forecast generally very low for individual month, on an individual month basis, which is not surprising because we really can't forecast rainfall that well, climate that well. So the skill tend to come from the impact of your initial catchment condition, and that skill tend to come from the initial few months. And usually the skill is better at the recession when your hydrograph goes down. But we do, for some locations, we do have some skill in rainfall, and therefore that also carries to longer lead time. Now, these last two are quite interesting because they're for Tasmania, and the Hydro Tasmania, they've been trying to do seasonal forecasts for many years, and they came to us, they said, well, can you help us? And using the BJP method, we looked at it, we said, look, there's no skill for your catchment. What's happening with the Tasmania is they have very rocky mountains, but also very thin soils, and also very wet conditions. So you really need to get your rainfall, because anything falls will run. So you need to get your rainfall forecast right. Your catchment doesn't have a lot of memory, so you really need to rely on rainfall. And for Tasmania, happened to be a place very hard to forecast rainfall. And we also show very consistent results here in terms of the Tasmania results. However, the good story is on the cumulation. We actually get a fair bit of skill. So we still have a few red spots, but we're sort of trying to refine those. But by and large, we actually got quite a bit of skill in terms of forecasting the accumulation, which I mentioned that we think this is probably more relevant for the water resources management. With that results, we're quite pleased. Now, in conclusion, the Fox model for Ensemble forecast monthly Streamflow. So we developed this model in the last year or so. So we are still refining that this year. And we use the Cband method to PostProcess GCM climate forecast for use in the catchment water balance model. We think the Cband methodology is reasonably mature. We applied it to catchment scale, we applied to continental scale, and we applied to monthly, seasonal, applied to short lead time, longer lead time, and we applied to Australia, applied to China. And just last week, we were working on a proposal with NOAA Climate Prediction Center, and we're setting up a project to evaluate the application in the US of the Cband method. Forecast monthly Streamflow generally skillful only at a very short lead time, as you've seen from the 20 catchments. However, for the accumulation, we're getting some decent skills, which we think there's enough information useful for water management planning, for those planning models. I guess in terms of science, we're really pleased that the forecasts are statistically reliable in uncertainty spread for both individual month and accumulation. And what that's telling us is the Fox is representing the rainfall forecast uncertainty right, the hydrological uncertainty reasonably well, and the position in the Streamflow, and propagate that from lead time 0 to lead time 12. So, we quite, so the actual methodology I didn't really elaborate today, but we think we've made some progress there in terms of the science we've done. So I think pretty much now we actually developed a model, and that generates the sort of forecast the water industry has been telling us that's what they want. And I look forward to working with Julian and his colleagues in the Bureau of Meteorology. I think this stage, the thinking is next financial year. So this year they're doing the merging work and getting the merged forecast out to rest of the users. But next financial year, we're starting to work on this, to deploy this. So I see this as a major leap from the current 1 month, first month forecast, and then 3 months total, so which 2 products after the merging is done. So this one would actually provide Ensemble 12-month time series. Thank you.